now?
Yes, your presentation as well.
Okay, so what I'm going to speak today is a rather popular subject, the 6 degrees of separation. And this is a study that we conducted some year ago, 3 years ago, practically was published in PRX, as you see at the end of the slide. And it involves a very interdisciplinary collaboration involving not only network scientists, but social science people, strong mathematicians, because it's based on the proof of 7 theorems, as you will see, and also people that are strongly involved in the structure and dynamics of networks from the point of view of game theory. So let me introduce a little bit the motivation of this work. The story, 6 degrees of separation, starts 100 years ago. This is 1920, and it does not start in science. It starts by a novelist. This Frigyes Karinthy is a novelist, he's an Hungarian novelist. And in 1929, he wrote a novel called Chains. In this novel, he describes a group of friends which are discussing among them how the members of the human society are closely tied by their network of acquaintances. And actually, one of the participants of the discussion proposes that any person in the world, at that time the world population was 1.8 billion people, could be reached by any other using a chain in this network of acquaintances of no more than 5 individuals. So that's the idea of 6 degrees of separation, that you are separated by any other person in the world by maximum 6 steps in the shortest path that you have inside the network of acquaintances that is mapping the human society. So this story has nothing to do with science. I repeat, it's a novel, coined the expression 6 degrees of separation. And then they started to interest science because in 1967, the first experiment on social distancing was made by Stanley Milgram. What Milgram did, he took 1,000 farmers. You probably see my mouse in Nebraska, a center state of the United States. They were farmers, and gave to each of them the goal of reaching a broker in Boston. So there was no chance that a farmer in Nebraska could know directly the broker in Boston. So what Milgram asked them to do is to write a letter to one of their friends whom they suppose is closer to the target. And upon receiving the letter, the friend had to write a second letter to one of his friends, whom this time he is supposed to be closer to the target, and so on and so forth, up to constructing the chain from the farmer to the broker. And so he constructed these 1,000 chains, and he then made the statistics of these 1,000 chains and found that indeed the number of letters that had to be sent in the chain, so the number of intermediaries, was indeed around 6. The same experiment was repeated in 2003 by Duncan Watts at the Columbia University, but this time with email addresses. So in this way, a much larger statistics was created. 24,163 chains were constructed, aimed at different targets from different countries. And once again, the average number of steps in these chains was around 6. So once again, this number 6, magic number 6, comes out. Of course, then we live in a world which is made of social networks. So there are several experiments at the planetary scale on social networks. And, for example, 2007, Yuri Leskovich and Harry Horvitz started to analyze a data set of 30 billion conversations among 240 million users of Microsoft Messengers. And they again revealed that the average path length was 6. 2011, Twitter, now X, was analyzed, and it was found that the average degree of separation between two randomly selected users of Twitter was less than 6. Finally, Facebook. Facebook is today the third nation in the world after India and China. There is Facebook with about 1 billion users. At 2011, the users were 721 millions, and the number of links were 69 billions. Okay? So again, this is a tremendously huge network. You could analyze this, and then once again, you can find that the average distance between the nodes is smaller than 6. And now you have a problem. What is the problem? The problem is the following. If you compare the 1,000 farmers of 1967 experiment on social distancing with the 721 million users of Facebook, you understand that you have about 7 order of magnitudes between these numbers. Now, what you know is that if I grow a network on a regular structure like lattice or a ring, the diameter, which is the maximal distance between the node, is which is the maximal number of steps you have to do to reach any two nodes, the diameter of the network scales linearly with the sides. So if it is 6 for 1,000 people, it should be enormously larger for 721 million people. And it is not the case. It's still smaller than 6. Well, but you can argue that we are living in a small world network, there are scale-free networks, blah, 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 whatever. But the very established results is that small world networks, Erdős-Rényi, scale-free, they all have the property that the diameter scales logarithmically with the sides. Once again, logarithmically is not linearly, so the increase is much slower, but in 7 order of magnitude, you should see the difference. So if it is 6 for 1,000 people, it should be 82 for 721 million. And instead of being 82, is smaller than 6 again. So the problem is, how is it possible to have a model, a generic model, in which I can grow a network in a way that the distances are renormalized all the time new nodes arrive? That is, in a way that the diameter of the network is independent on the sides. Does not depend on the sides. If I double the network, the diameter is the same. If I triplicate the network size, the diameter is the same, and so on and so forth. So if you want a sort of ultra-small-world or hyper-small-world property, in which the diameter is not scaling with the sides. And so this was the motivation that started our study. And as you will see very soon, we can show how this is possible. And when we will show that this is possible, we will also show that the only way through which this is possible is that the diameter is 6 and not 7 and not 5, but right 6. Okay, so let's go on. So the idea is, that networks are divided into 3 main categories. You have the biological networks, the technological networks, and the social networks. So we start to say, what is the characteristics that characterize social networks? And this is the fact that social networks are made of rational agents, made by people. This is not the case of technological networks, which are designed by somebody, or of biological network, which are instead fruits of evolution. In the case of social network, you have rational agents. So it's normal to assume a game theoretical approach. That is, imagine that the network evolution, the network growth, is in a sense ruled by a game. A game in which each agent, that is, each person of the network, has a cost, has to suffer a cost in forming or maintaining a connection, and at the same time, it has the benefit of having that connection. So each connection determines a cost, but also determines a benefit. And so the idea is that, in a sense, a rational agent balances this cost and benefit and decide to make the connection, whether or not to make the connection, depending on whether the cost is larger or smaller than the benefit. Okay? Just to show this in a model, imagine that each agent, the end nodes of a network are the agents of a game. So the agent of the game is this lady, this red lady. And at each step of the game, the red lady has a given neighborhood of actual friends. Is connected, in this case, with a blue man, with a yellow woman, and with a pink man. But at this time, so at each time of the game, the agent asks, is for me convenient to stay with my actual friend or to move to another neighborhood? So I have a second neighborhood, which is potential new friends. They are potential new friends. And as you see, the neighborhood include part of the actual friends, but some other which are not contained in the network of the actual friends, or also somebody that was in the actual friend is not, a different group of person, and has to decide whether to stay with the actual friends or to move. And in order to decide, what the agent does is very simple. The agent asks, how much would it cost me to connect myself with the new friends? From one side. And from the other side, the agent asks, how much benefit would I get from the move? Now, if the benefit is smaller than the cost, it means that this move is not convenient. So I stay with the actual friends. I don't move. And you see, in this case, if the benefit is smaller than the cost, the red woman stays with the actual friends. Otherwise, if the benefit is larger than the cost, it means that the move is convenient for me. And then I move. Very simple. Okay, so the rule of the game is moving or not moving depending on benefit and cost. So what you have to do is to define a cost function, a benefit function, and to run the game. So for the cost function, it's reasonable to assume, I repeat, I'm now here trying to put a sort of zero model, so very simple model, archetypical model, then one can make all kind of refinements of the model. For the cost function, it is reasonable to assume that each node has to pay a unitary cost, C larger than zero, to maintain a connection. So what we assume is that I am node V. I want to establish a connection with node U. I pay this cost C. You cannot refuse my connection. And that's all. Of course, this is a very, very simplified case. It's not the case of Facebook, for example, because you have to ask the friendship and the other one has to accept. So the benefit, the cost and benefits has to be mutual, not just. But in this case, let's assume very simple. So I have to incur a cost C. I pay for this cost C, and that's all. For the benefit function, once again, we were, so to say, inspired by social network. What is the goal of the member of the social network? Is to become influencer. That is to become central in the flow of information of the network, or if you want, is to increase their visibility inside the network. And this is naturally framed by the betweenness centrality. So what is the betweenness centrality? I am node V. I take node S and T different than V. I consider the shortest path in my network connecting S and T. This shortest path can be more than one. I mean, can be multiple. There can be multiple shortest path. So sigma st is the number of shortest path that are that connect S and T, and sigma st of V is how many of such shortest path are passing through node V. So this quantifies how many shortest paths are using U, node V, as intermediary. And then you sum up on all possible pairs S and T. In this way, you calculate how much node V is central in the network, imagining that the flow of information between all possible pairs in the network are navigating by means of shortest path. Actually, instead of these distances, we use something a little bit different because in a more realistic case, you have to weight the shortest path, with the length of the path. Because if you are the only intermediary between S and C, your importance is very high. If instead you are one of the 100 intermediaries between S and C, S and T, your importance should be lower. Therefore, what we do, we take the formula of the betweenness centrality and we multiply by a function which is a strictly decreasing function of the argument. The function is the function of the length of the shortest path between S and T. Okay, so we obtain the weighted betweenness centrality, which is the betweenness centrality in which you take into account that if I am the only intermediary, this function f L will be 1, okay, or 2, sorry, because I'm the only intermediary. So f of 2 will be very large. If I am one of the 100, L will be 101, so f of 101 will be smaller, and so I weight this contribution. So you can think, you see, at the end of this weighted betweenness centrality as follows. You have each pair of nodes S and T in the network generates some utility, and this utility is distributed equally among all shortest paths from S to T. Therefore, each intermediary vertex in each path obtain a fraction which is FLST divided by sigma ST. So this is very simple. So you use benefit function, the betweenness centrality, the weighted betweenness centrality, and cost function, a constant. With these two choices, you can run the game. And what happens? It happens that you start from some initial condition, and then the game try to arrive to obtain what is called the Nash equilibrium. What is the Nash equilibrium? The Nash equilibrium is a configuration which is stable, which cannot change, because in this configuration, no agent has anything to gain by changing the neighborhood. So it's a configuration in which you cannot change anymore, because any change you make generate more costs than benefit always. Okay, so if you want, is a situation in which each node found its optimal neighborhood given the choices of all the others. And then in our paper, we demonstrated 7 theorems in which we proved that this Nash equilibrium has the following 2 characteristics. Number 1, the structure of the network that emerge eventually contains at least one vertex, we call it V, of very large degree. So it has a hub, at least one hub. And this is not the problem in social network, because social network have many hubs. But the most important thing is that this node V, is at the center of the network because it has the property of being at a distance no more than 3 from any other nodes. Okay? What does it mean? It means that you have the 6 degrees of separation. Because if you take any pair of nodes from the origin node, you need at most, 3 steps to get into this node V. And then from node V, you need another maximum 3 steps to get to the destination node. So it means that you take any pair of nodes, the maximal distance that you can have is 6. And it's independent on the sides. So you see, the later property implies that the shortest path within any pair of nodes will be smaller or equal than 6, and therefore you have the spontaneous emergence in the Nash equilibrium of the 6 degrees of separation. So why 6, not 5, not 7? Because 6 is equal to 3 times 2 in this case. If you are interested in all the technical details, I'm sending you to the supplementary material of this paper in which all the theorems are explained. I want here to give you the idea why this is happening. Why this is happening, and in order to do this, I have to introduce, actually not to introduce, but to extend a definition that is present in classical graph theory. In classical graph theory, a one independent set, which is also called sometimes internally stable set or anti-clique, is the set of nodes such that there are no connection among them. If you look at the figure in this slide, you will see that nodes A, B, C, D plus the blue node form the one independent set, because you take any pair of, for example, B and this blue, there is not a link. A and B, there is not a direct link. A and C, the same, C and this blue. So if you take any two pair of the members of the one independent set, there shouldn't be a direct connection. And so as a consequence, any pair of vertices that are in this one independent set, by definition, they have a distance which is strictly larger than 1. And now let us generalize and introduce the definition of L independent sets. L independent set is the set of nodes such that their distance is strictly larger than L. For example, let's consider the 2 independent set. And if you look at the figure, you will see that A, B, C, D are in the 2 independent set, because 2 independent set means that there is not a direct link nor a single intermediary. You need at least 2. And indeed, if you take A and B, you have 2 intermediaries, the 2 red. Same for AC, same for AD. Whereas if you look, for example, the blue node, you see the blue nodes are not members of the 2 independent set, because this blue node and D, they have 1 intermediary. So it is clear, therefore, that you can define L independent set, and it's clear that if you are a member of SL, you certainly are a member also of SL minus 1. So if you are a member of the 2 independent set, you are also a member of the 1 independent set. But the vice versa is not true. That is, you can be member of the 1 independent set, but not of the 2 independent set, like the 3 blue nodes that are depicted in the figure. Okay, so then, go on. Now consider these 2 situations. Consider the figure A here. I have node 1 and 2, which are in the 1 independent set. So this means that there is not a direct connection, but there are many nodes like 3, 4, 5, 6 that provide connection among these 2 nodes. And now imagine that an external node, node 7, decides to bridge 1 and 2, to make connection to all the members of the 1 independent set. So 1 and 2. This is a legitimate move. And this move should be prohibited in the Nash equilibrium, because otherwise you're not in the Nash equilibrium. Now the question is, how much is the gain that node 7 does in creating the two yellow connection? And the answer is very little. Why very little? Because if node 7 forms the two connection, node 1 and 2 remain in the one independent set. The only things that change is the multiplicity of the shortest path. So before there was the shortest path through nodes 3, 4, 5, and 6, and now there is also node 7. So what node 7 gains, I mean, it has to be divided, split with all the already existing shortest path. You understand? So the quantity of the betweenness centrality that is obtained by node 7 in doing this is very little. And since it's very little, it means that given a given cost C, there will be a size in which this indeed will be prohibited. So this means, if you want, that large one-independent set are compatible with the Nash equilibrium. The Nash equilibrium can contain large size one-independent set. And one of the theorems is indeed how much is the size of the one independent, the maximum size of the one independent set can stay in the Nash equilibrium. Now, a completely different situation occurs in the situation B. Now we consider node 1 and 2, which are in the two independent set. Okay? In the two independent sets. So there are no direct connection, not single intermediaries, but you have 3A, 4B, 5C, 6D. And now we do the same. Node 7, bridge, node 1 and 2. And again, we ask how much is now the gain of node 7. And now the answer is the gain is tremendously high. Why? Because when node 7 forms the two yellow connections, the node 1 and 2 are removed from the two independent set. And they pass to be in the one independent set. Okay? And actually, 7 is the only intermediary. So 7 takes all the gain that previously were in the other shortest path, 3A, 4B, 5C, 6D. All the amount of utility that was in those shortest paths is now taken by 7. Because 7 is the only shortest path. Now the shortest path is not anymore 3, it's 2. So this means that this move is tremendously advantageous, and therefore this means that the Nash equilibrium cannot have two independent sets. Two independent sets are prohibited in the Nash equilibrium, because if you have a sizable two independent set, you will always find a node for which is convenient to bridge them for any cost. And this is another theorem that shows this. And now once you demonstrate that the Nash equilibrium cannot have two independent sets, it's now, the question is, can a node question mark exist at distance 4 from node 7? From the famous node 7. And the answer is no, because if I have such node question mark, then it means that from node 7 to question mark, I have to construct the shortest path with 4 steps. So it means that I have 7 with 2, 2 with A with something else, and this with question mark. But then if this is the case, then question mark would be in the two independent set with 1 and 2. And so 7 will bridge also this node, as I just started to demonstrate to you. So this means that you have the network tends to find this centralized hub. And since you have this property, then you have that this node 7 is at distance no more than 3 from any other node. And therefore, you have the emergence of the 6 degrees of separation. So this is the main idea in how you can build and grow a network such that it maintains a constant diameter, independent on the sides, and equal to 6. Now, this is everything. So let me show you with numerics. We did a very, very huge numerical trial. In the horizontal axis here, you have the sides of the network. we start from next of few nodes, and then we arrive to 10,000 nodes. For each value of n, what we do, we create an ensemble of 10,000 realization of the Barabasi-Albert network. Why Barabasi-Albert? Because it contains hubs, so it's a good initial condition. You can take any initial condition you want to play your game, but sorry?
그런 경험을 해보고 싶어 그냥 막연히 어차피
Sorry? So you can take an initial condition, but taking an initial condition with already hub, it's facilitating the convergence to the Nash equilibrium. So you have an ensemble of initial condition. On this ensemble, you take the average diameter, and this average diameter is the blue line. Here, you see, it's a blue line, which if you report in a linear log scale, in a log linear scale, is a perfect straight line. So it means that it grows logarithmically with the size exactly as one should have expected. Then each one of these initial conditions, 10,000 for each size, are taken as initial condition of a game. We evolve the game, we let the game to arrive in the Nash equilibrium, and we obtain 10,000 Nash equilibrium of that size. So we obtain another ensemble, which are the final state, the equilibrium state of these initial conditions. We measure, which is the green line. We measure there the average diameter, and you see it grows up to 6, and then it stays 6 together. So this is an ultra-small-world set. One can question, and a very good referee questioned us saying, okay, but if you start from an initial condition and you arrive to a different configuration, you're changing the density of the network because you're adding links and removing links. So it's evident that also the average distance is affected by a different density. So what we did, we went back to the initial condition. We repeated the game up to obtaining the Nash equilibrium, but then we took note of how many links were added and how many were removed. But the net is adding. So how many extra link you have? And then we went back to the same initial condition and we added exactly the same number of links, but this time randomly, without comparing cost and benefits. So we obtain a third ensemble of 10,000 networks, which have the same density of the 10,000 Nash equilibria in the green line. And this is the red line. So we start from same initial condition, and we add the same number of links, but randomly. And of course, what happens is that the red line is below the blue line. So you change and you reduce. But if you again plot this in a linear log scale, you see that also the red line grows logarithmically. So once again, the only way through which you can have an independence of the diameter on the sides is by means of the Nash equilibrium. Okay, so this is practically what I wanted to say. This paper opened a lot of discussion because now you can enrich the model with a lot of things, study realistic social networks. But I think the most important conclusion is this. You see, the compensation of cost and benefits is a natural interaction strategy of rational agents. So it's normal that we consider this in social networks, and this also explains why the 6 degrees of separation is seen in social networks. But imagine now to use the same principle for design, so for technological networks. You can, for example, consider air or sea transportation networks. So there you have airports and ports, which may increase their volume of trades and or tourism by being in between the main routes of interchanges. So therefore, they are keen to incur in the price of building new connections. So you have again the same principle of cost and benefits. And so you can use the same mechanism to design, for example, an ultra-small-world configuration for transportation network, which may be, for example, useful for distribution of goods. You are sure that any good starting from any place in the world will reach any customer in maximum 6 steps by doing this independently on the size of the market and so on and so forth. What about biological networks? Biological networks, of course, are not rational agents. Proteins are not rational agents. Genes are not rational agents. So one cannot argue that the betweenness centrality was the main motor or main reason why the shape of the structure of such network is this, because this depends on million years of evolution. However, if you look at Darwinian evolution is done by 2 steps, the random mutation and selection. And selection is usually the most fit. So you have this random mutation, and then you have a selection mechanism. Therefore, you can imagine that the cost, but some benefit function could be other function of the network, say the resilience to random perturbation. If you are more resilient, you are more fit. Or the local and global efficiency. If you are more efficient, if your mutation creates larger efficiency, then this is evolutionary advantages in terms of, and so compensating cost and different kind of function, not betweenness, but I repeat, resilience or efficiency, could generate a game, and this game could give rise to some Nash equilibria, other Nash equilibria, which are displaying the properties that you observe typically in biological network. The most important property is degree anti-correlation, so disassortativity. Can disassortativity emerge when you obtain, when you have from a game theoretical approach of this kind? This is something we are working right now. Thank you for the patience. If you have questions, I'm here to answer. I just want to make a little bit of publicity to Physics Reports. I'm editor there for the areas of nonlinear dynamics and complex systems. It's a very important journal, which is hosting monographies and review papers. So if you have proposals for reviewing a given subject, you can send them to me in a 2-page proposal form. There is no template, so you can do whatever you want, but the important point is that you include a tentative table, extended abstract, and most importantly, a 25-line rationale in which you say why it's important to have this proposal now, this review now, why this is a timely review and can attract and can be useful for, indeed, as the presenter said, for a PhD student that wants to enter the field. A tentative table of content, the name and coordinates of a corresponding author, and the tentative date of submission. And said so, I'm leaving the presentation and answering your question. Thank you.
Thank you, Stefano. So, if the audience has some questions, this would be a very nice time to discuss.
I have a question. Can you hear me?
Yes.
Yes.
Okay. First of all, thank you very much for the very interesting talk. I was wondering whether the generative model that you propose to recover the 6 degrees of separation also accounts for other properties of real-world networks. I don't know, about clustering and so on, or if on the contrary, it's especially devised only for the degrees of separation.
Okay, this is a very good question. It's also the question that was given by one of the referee, and we answered. Maybe it's you, the referee. No, I know.
Definitely not.
No. The model itself does not generate other things that normally are observed in social networks, like hierarchies, like clustering, and these things. The model as a zero model generate only the 6 degrees of separation. However, it does not cancel this. That is, if you start from an initial condition having a clustering coefficient, very high clustering coefficient, the resulting Nash equilibrium has more or less the same clustering coefficient, plus the 6 degrees of separation. So what I'm saying is that the model introduced the 6 degrees of separation. And if you start from an initial condition which is hierarchical, the Nash equilibrium will be hierarchical also. Okay? So that's we did indeed we used as initial condition the Barabasi-Albert in our numerics. Barabasi-Albert has zero clustering coefficient, zero things, but you can use initial conditions which are more sophisticated and prove that you slightly, of course, you change because you change some links, but you don't change fundamentally the nature of this. You don't add, you don't imprint these things. So what you imprint is the 6 degrees of separation.
Okay, thank you very much.
Any more questions from the audience?
Can
Okay,
you
so
hear me? Maybe I can ask
yes,
a very small question, so if
yes,
possible, if you have time.
of
So it's
course,
very
Jay.
nice. Thank you very much. So, and then I like this numerics and then everything very much. And then for the theorem, so I do have a question. So you say strictly decreasing function you choose for f when you basically do this optimization between
Yes,
the cost of benefit and the cost and then
yes,
benefit. And then there, as far as I understand, you're choosing one like 1 over L alpha.
yes.
This is very nice.
This is sorry, I'm not. Yes, I'm sharing. You should be should see my screen now.
Correct.
So for the numerics we used as strictly decreasing function 1 divided power alpha
Yes. And
of
then
the
also you choose cost parameter C,
and
correct?
the cost
And then
parameter C for the numerics is chosen to be constant.
correct. Yes, exactly. It's a linear cost. So that's also perfect. And then to me, I mean, so it's very natural selection. But I believe if you do choose this f to some different strictly decreasing function, then I don't think the 6 will be the universal number. Is it
Okay, so
correct?
this is no the for any strictly decreasing function you get 6. The
Oh,
problem is another. The problem, I have no time to enter in detail, but it's written in the paper. The problem is another, is that
okay. I
in
can
order
check
to
it then.
calculate between the centrality and the other one, the weighted business centrality, node V must know the entire structure of the network because it has to take all possible pairs and calculate the shortest path. Now, in normal condition, it's not reasonable that one single member of the social network knows all the structure of the network. You
Correct.
know? So what is normal to imagine is that a given node has a limited horizon of knowledge of the network. So he knows the first neighbors, the second neighbors, the third neighbors, and so on. You know? And so what you can prove here as a theorem is that when you have a limited number of knowledge, so you know your friends, the friends are your friends, and the friends are your friends are your friends, but you cannot know more than this.
Okay.
Then the final diameter in the Nash equilibrium is always twice h,
Yes.
where h is a constant that is satisfying this inequality.
Exactly.
Okay?
This is exactly
So
what I also see. Yeah.
6 is, but it can be 8, it can be 10.
Correct.
What
Yeah.
cannot be is 7 or 5.
This is definitely, I understood. Yes, exactly. That was my question. So basically, if you choose this, I mean, so if you basically set
Yes,
these things
and
according
indeed
to
now
tree, then
we
yes.
are
Okay,
demonstrating
perfect.
other
Yeah,
theorems. We are working with our Russian, because
yeah,
mathematician, you need the Russian mathematician to do this.
yeah. I understood. Yes, thank you. Very good. Yeah. So, I mean, if it is like a slow decaying or faster decaying, in this case, you can somehow set this age to some different number. I understand it has to be
Yeah, but
even
of
at the end
course,
of
in
the
order
day,
to
but
publish on Physical Review X, you have to prove 6 because 6 degrees of separation is so popular,
I
and
mean,
the
so
narrative
that was
comes.
my feeling. Thank you very much
Yes.
for saying it, like articulating it. So
Okay.
thank you. Yeah, so very nice. Thank you.
Thank you. If no more questions, maybe I know that Stefano's a bit in a hurry, so
Well, I am out of town and I have to go back
yeah.
home. So the moment I finish, I will leave you. And but if you have any other question, what I suggest you to contact me. Probably you can share my
Sure. Yeah.
email.
I
My
will do that in
email
the chat.
is very simple. Is Stefano.Boccalleti, my name dot my surname at gmail.com. So you can contact me for anything.
So with that, if there are no more questions, I would like to thank Stefano. Thank you for joining us, Stefano. And with that, we could conclude the 11th BeyondTheEdge Seminar series.
Bye bye. Thank you.
Bye bye. Ciao.
Thank you,
Bye.
Stefano.
Ciao.
So